Hello, today we're going to start chapter 6, which is about statistical distributions. This is using a lot of maths you've already met, but haven't met it being used for probability. So, a couple of things that we need to define first. A random variable is any variable that we can have as our outcome for our event. So this needs to be a numerical thing. So it's not heads or tails, but it might be number of heads or number of tails. A sample space, that's just all the possible outcomes this variable can take. So if you flip 3 coins, the number of heads you could have no heads, 1 head, 2 heads, 3 heads, but you can't get any more than 3 heads if you toss 3 coins. A variable, that's the thing that we can have, which might be the number of heads or number of tails. It's discrete. We're going to stick to discrete distributions here, so we're after 3 heads or 4 heads. You can't have 3.5 heads. And this is completely random, so it's not like if one coin flips and gets a head, the other one automatically gets a tails. We don't know what this outcomes are going to be until the experiment's been carried out. So, there are a couple of different ways of representing these discrete probability distributions. The first one, we could write it like a function. You're probably used to seeing a function as f of x, and it tells you what you put in. So here x is the score when our dice is rolled. So probability that x equals, and x here can be 1, 2, 3, 4, 5 or 6. So probability that x is 1, that will be a sixth. X is 2, that will be a sixth. X is 3, that will be a sixth. And that's what we'd expect for a fair dice. We could also put this information in a table. Here you can see the different scores we can possibly get for x and the different probabilities associated. So if we want to know the probability that x equals 2, we go into the 2 column for x, we look up the probability, we get 1/6. We could also do it as a diagram, so this is like a chart. Here you'll see the different x values and the probabilities associated 1/6 for each of them. These 3 things are different ways of representing exactly the same information. So you could do it as a function, a table, or a diagram. And you might be given a diagram and asked to draw a table, or given a function and asked to draw a diagram. There's one more important thing to realise, because it's still probability. If you add up all the probabilities, you get to 1. So if they gave you 5 of these things and 1 blank one on the end, we could use that. All the probabilities add up to 1 to work out what the missing thing is. For the first example, we've got 3 fair coins are tossed. And A asks us to write down all the possible outcomes when the 3 coins are tossed. So we could have heads, heads, heads. That would be a possible option. We could have heads, heads, tails. We could just list these. We could put them in some kind of a grid or an order. But let's just start listing. So we've got heads, tails, heads. We've got heads, tails, tails. And then we've got all the other ones. So I've done heads first and then 2 heads, 1 head, either way round, 2 tails. So we've got tails, 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 heads, tails, heads, tails, and tails, heads, heads. So these are all the possible different outcomes we can get when we toss 3 coins. Our random variable x is the number of heads. So you can see in this one it's 3. This one it's 0. So write down the probability as a table. So our probability distribution. So a table, we're going to have probability x equals our little x here, and our options for little x here. And I'll fill out the rest of the table after we're done. So options for x, we could have no heads in this case. 1, 2, or 3 heads. So I'm now going to make this into a table. Okay, so the probability of getting no heads is just this one, so it's 1 out of 8. Probability of getting 1 head, that would be this one and this one, so that's 2 out of 8. This one is also 2 out of 8, and this final one is 1 out of 8. The only possible outcome here for 3 heads, which is this one. To write this as a probability mass function, we're going to say probability x equals x equals, now there are 2 possible outcomes. It could be 1/8 if x is 0 or 3. and 1/4 or 2/8 if x is 1 or 2. And you can use commas or you can use or for this. Either of these is fine. So here we were asked to do two different versions for b. This bit here is part b. We can do it as a table here, and we can do it as a function here. So function, we just say what our probability is and our two different options and the x values associated with it. And we can see here that our 0 and 3 correspond to 1/8 in here, and our 1 and 2 correspond to 2/8 or 1/4 for this bit. So that's how we do probability distributions. For this one, we're given a model where we have a four-sided dice, and this four-sided dice we've not been told that's fair, we've actually been told that it's biased. So we get given a formula here, so this is a function and different values of x that we can possibly roll, and we're asked to put this, or find the values of k. So the probability that x equals 1, all I'm going to do is I'm going to put 1 into this formula up here, is 1 over, so it's k on the top, and the x value here is 1. Notice if I want x is 1, I put 1 here, and I put 1 here on the bottom as well. Probability x equals 2. Let's just get this to refocus. Apologies. So if we're after x is 2, we're going to put 2 in here, so we get probability x is 2 is k over 2. So by putting the 2 in here for little x in both this bit and this bit of the formula, you'll notice for probability x is 3, we have k over 3, and for the 4 one, we have k over 4. And these are all the possible outcomes, so we know all of these probabilities must add up to give us 1. So we have k over 1 plus k over 2 plus k over 3 plus k over 4 must equal 1. Because we've got quite a lot of fractions here, I'm actually going to multiply everything by 12 to get rid of all of these fractions. So if we do, we'll get 12k here, plus 6k, plus 4k, plus 3k equals 12. Adding up these numbers here, we get 12, 18, plus 7, we get 25k equals 12. We get k is 12 over 25. So this is just from the fact that all the probabilities must together add up to 1. We're now asked to put this into table form. So our options for x are 1, 2, 3, 4 from here. So we've got x on the top, and we've got probability. And we've got probability on the bottom that our variable is our value little x. So our options on top are going to be 0, 1, 2, 3, 4. Actually, there's no 0 option for this. Let's get rid of that one. Fill in the rest of my table. And we can start working out the rest of these probabilities. So the first one is k over 1. And if k is 12 over 25, that's just going to be 12 over 25. This is k over 2, so this is like a half k, so this is 6 over 25. This next one is k over 3, so it's going to be 4 over 25. And finally k over 4, so it's 3 over 25. So we did this simply by looking through our probability distribution, working out all the different probabilities, adding them up to 1. So because we set this equal to 1, we could work out the value of k. We're then going to put our k back in here, so it's k over 1, k over 2. So I just took this 12, divided it by 2 to get a 6. If you wanted, you could do this on a calculator. For the final bit of the question, we're asked to do a couple of probability questions from our table. So this first bit asks us to find the probability that x is greater than 2. So this is the option for 3 and the option for 4. So for C, over here, probability x is greater than 2 equals, so this is greater than 2, this is the option for this for 3 and this for 4, so together this is 7 out of 25. For the next part of C, we're asked to do probability 1x less than 4. So the only options that fall into this category are options for 2 and options for 3, because we're strictly greater than 1 and strictly less than 4. So this is the 6 plus the 4, so this is going to give us 10 over 25, or 2 out of 5 if you cancel down. For the final one, we're asked to do x is greater than 4. There are no options for x is greater than 4, so the answer to that one is 0. These questions might look quite straightforward. It might be slightly confusing way of writing it, but this is all, can you use your sum of the probabilities equals 1 in this new function and table notation? So have a go at a couple of the, there's another example to do. Okay, so here we've got a spinner, and we're going to keep spinning this spinner. It's got 3 blue and 2 red sections on it, and we're going to spin this until it's been spun 4 times in total, or until it lands on red. And we're asked to find, it's S, not T, S, which is the number of times this thing has been spun. So the options for S, we're going to write out probability S equals little s, and here are our options little s. What options can this thing have? It could spin it once. We can't spin it no times, because that was not going to be landing on red, or spun 4 times. So 1, 2, 3, or 4. And we need to work out the probability for each of these things. So the probability we spin it once is just the probability we get red on the first attempt, which is 2 out of 5. This next one is 3 out of 5, so we spin a blue, times 2 out of 5, so we spin a blue and then we spin a red on the next one. So this is 6 out of 25. This next one is red on the blue on the first one, times another 3 out of 5, times 2 out of 5, which is going to give us 9. It's going to give us 18 out of 125. So that's that gives us 9 times 2 is 18, and then 125 on the bottom. For the very final part, this would be the probability of getting to 4 things and either getting a red or getting blues for the first 4 attempts, and then we stop. We're actually going to use the sum of the probabilities equals 1 to work out this last thing. So if I add up the 2 probabilities we've got, or 3 probabilities we've got so far, so this is 2/5 plus 6/25 plus, and then we get 18 125ths. And I add these up, I get 99 out of 125. So if I do 1 minus ants, we get 27 out of 125. So the most difficult one here we actually worked out by doing the sum of the probabilities add up to 1. So this one is 1 minus total of the other 3. So if there's one that looks particularly difficult, don't work that one out. We can always work out the 3 easy ones and then do 1 minus answer to get your final one. So here they asked for the probability distribution. They didn't specify a way of doing it. I could have done this as a function, but tables are usually the easiest way to do it, so I chose to do this as a table. For the final part of this, and to get some practice, we need to have a go at exercise 6a. Quick reminder that you can get all the full solutions online on the textbook section of Moodle, as well as answers in the back part of the book. For the next little bit, we need to mention the discrete uniform distribution. This is actually part of Year 1 stats, but it's not in the textbook because they've actually missed this out. The discrete uniform distribution is a really boring distribution where every outcome is equally likely. So things like scoring a fair dice, all of the options 1 to 6 all have a probability 1/6. So it's anything that looks like this. Score on a dice 1 to 6, probability of 1/6 for each of them. So it's called uniform because all of these probabilities are the same. There aren't really any questions to do about it. You just need to know that the discrete uniform distribution means all of the probabilities are the same. So have a quick think, pause the video if you like, and have a think, which of these are a discrete uniform distribution? So tossing a fair coin once, recording the number of heads, that would be a discrete uniform distribution. Tossing 2 coins, if you're recording numbers of heads for instance, this is not going to be a uniform distribution because the probability of getting 1 head is actually different. It's actually more likely that you get 1 head rather than no heads. Shoe size, there's definitely a median shoe size that's more popular than everything else, so this is not going to be uniform. Same with height. Month of birth probably is going to be quite uniform. There are slightly more people born in September and October, but roughly uniform. However, the day of birth, things like the 30th and the 31st are going to be very underrepresented. So this month of birth, fairly similar to a uniform distribution. Day of birth, there's going to be some fairly drastic differences for things like the 31st because there really aren't very many 31sts. Just to make you aware, in reality you won't get perfect results. So these numbers here, if they were rolls on a dice, and this person, me, my initials, asked them for their favourite number between 1 and 5, this is actually fairly uniform because they're all pretty much about 90. So this actually looks quite good for the discrete uniform distribution because none of these results differ massively. I mean, we've got a difference of 3 here between the highest and lowest, but they're all roughly the same. Whereas if you were to look at data like this, which might be the number of maths practice papers people were doing each week, this is definitely not a distribution that we could use for uniform distribution because the frequency numbers are very, very different. So this would suggest there are quite a few people doing a few people doing more than 4, but most people doing 2 practice papers, which is probably the right amount to do in the run up to exams or end of year tests. So this is definitely not a uniform distribution because there's a big difference between the 0 and 4 values compared to 2. But this one, even though there's a small difference, this is a uniform distribution. Isn't that hard to believe? Sometimes when you actually do an experiment, you get a slight deviation from uniform anyway. If I ask you to roll a dice, you're not going to get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. You're going to get slight variation away. But you wouldn't expect to get 100 6s if you rolled it 100 times. Okay, we're going to have a quick look this lesson at the binomial distribution, which we'll continue into next lesson. This is using your binomial probability, so your binomial distribution, your binomial expansion formula, to try and work out what happens when we have repeated numbers of successes and failures. So if you think about it, when we do probabilities, we multiply together. So if you want like 3 successes and then 2 failures, you'd multiply the success 3 times and then the failure twice. For this, though, we need fixed probability of success. So not things like sampling without replacement where the probabilities change, but we're going to have a fixed probability of success, so we can multiply the probabilities together, fair and independent trials, a fixed number of trials ends. This might be a case of rolling 10 dice or taking a token out and putting it back 6 times to see which token you get. We're going to have 2 possibilities for this. We're going to have success and failure. So success might be getting ahead or drawing a red token out of a bag or anything else you might want to do that you can have as a repeated number of trials. There is a formula here which we can use from the formula book, which links the probability that we get a certain number to that number of successes, the remaining number, because if we do it n times, with P probability of success, if we have R successes, maybe 3 successes, we're going to have to work out how many failures that is. This first bit here, this is an NCR thing, which lets us know the number of different ways of getting maybe 3 successes and 2 failures. So this is just a binomial coefficient, and we've done this quite a lot when we do binomial expansion. We could actually put the numbers in the formula ourselves, or we could use the binomial function on the calculator, which is what we're going to have a look at in a second. So this uses the binomial expansion, but we're probably not going to be doing expansions for this, because in the exam you don't have time. They know you've got one of the ClassWiz calculators, and they know you can look it up. So this is going to be a 1-mark question. And if you're spending your time doing binomial expansion to work these out, it's going to take you far too long. So the calculator method, we're going to go to distribution mode, and we're going to go, which is mode. So if I go to distribution mode, we'll see it's here. It's mode number 7. We're going to go to binomial PD, which stands for probability distribution. For, we want just a single variable. We don't want the entire list, so we're going to click variable, and we can fill out all the different things. So we've got to specify x and n, which is the number of possible attempts, and p, which is the probability of success for any one attempt. This is best seen by having a look at an example. So we're going to have a look at this one. So here they give us a binomial distribution. So here they say x up here follows a binomial distribution where n is 12 and p is 1/6. So here we can get, I'm just going to make a note of these, n is 12 and p is 1/6. So we can work out from here, if I put in my x equals 2, which in the question we were asked to do the probability that x equals 2, if n was 12, and our probability is 1/6. If I put this in, it will turn the 6th into a decimal. If I press equals, it will tell me what the probability is of getting 2 successes out of 12 attempts if your probability of success is 1/6 for each of them. So for A, this is 0.296. We're going to go to 3 significant figures for each of these things. So we should probably write down what this is. So this is A probability x equals 2 is 0.296. So this is the probability, 12 attempts, a probability of 1/6 of getting a success, of getting 2 successes. So actually this is quite high, because you wouldn't expect to get very many successes if your probability of success is only a 1/6. Probability x equals 9, we're going to press equals here, we're going to change this 2 to a 9. Actually, this is a standard form number, so this is very unlikely. If you've ever got 1/6 chance of success and you're only doing it 12 times, to get 9 of these is going to be incredibly unlikely. So B, probability x equals 9 is 1.29 times 10 to the minus 5. So this is very unlikely. For C, in order to do the probability that x is less than 1, or less than or equal to 1, we need to do probability that x equals 0 plus the probability that x equals 1. Because if we're less than or equal to 1, then that leaves options for 0 and 1. We could have no successes or 1 success if we were asked to do the probability that we get 1 or fewer successes. So going back to here, we can put in 0 for this one, and we get 0.1122 plus, and then we can press equals again, we can put a 1 in for here, and we get 0.2692. We can add these two things together. If you go back to standard mode, the last thing we got will be the last probability, so that's this one. So I just need to add on 0.1122 to get my total answer. 0.381. So 3 significant figures for answers in stats. So here we use the calculator to look up these numbers. If you wanted, you could use the binomial powers thing to work out all of these numbers, but it's going to take you a long, long time. For this next one, we're given a question in context. So the probability that you randomly choose a person in a reading group and they're left-handed is 0.15. And a random sample of 20 members of the group is taken. Suggest a suitable model for our distribution. So A, we're going to use X is modeled by a binomial. So this notation here just says X is modeled by, or X follows B for binomial. The first thing in here is going to be N, which is 20. And our comma probability of success is going to be 0.15. If you consider a left-handed person to be a success. So X here is actually the number of left-handers. So we can work out here using our binomial probability distribution. So I'm going to go on distribution mode, select this mode here, and I'm going to go on binomial PD, which is option 4. And then variable, so I can work some things out. Exactly 7 of the members of the sample are left-handed. So for B, we want to know the probability that X equals 7. So I'm going to key in here 7, N is 20, and the probability 0.15. So I'm keying in X, N, and P. Press equals again, we get our answer, which is 0.10160. 3 significant figures. Remember, for significant figures, we're going to miss out this first 0. For BII, we're asked to find the probability that fewer than 2 members are left-handed. So this is X is less than 2, which is the same as the probability X equals 0 plus the probability X equals 1. Because we could have 2 successes or 2 left-handed people, no, 1 left-handed person or no left-handed people, and those are the only options for fewer than 2. To work these things out, we're going to go back to our probability calculator. We're going to put in 0 to work out the probability of no successes with 20 tests. So this is 0.03876 plus the probability for 1 success is 0.136799. Going back to normal mode on our calculator, that's the second one here, so I'm going to add on my 0.03876, press equals to get my total probability here of 0.176 to 3 significant figures. So here we had a problem in context. We've got randomly chosen members. We're going to assume these randomly chosen members are independent. It's not like the left-handers club. And the probability actually is 0.15 for each of them. We're going to sample 20 members, and we're asked to work out some probabilities. This fits with the binomial distribution. X is the number of left-handers. We've got 20 trials. We've got a probability of 0.15, so a P of 0.15, and X is the number of left-handers, which in this case we're going to call a success. We use this then to calculate probability X is 7, and fewer than 2, so probability of 0 and probability of 1, and we worked out these probabilities. Have a go at this exercise, which is on page 90 of the online textbook, which is exercise 6b. This is getting used to being able to pick out N and P from your question, and starting to be able to use the calculator to work out probabilities. Quick reminder with your calculator, make sure you are going on distribution, which is here, and then on binomial PD, which is option 4. In the next lesson, we'll look at binomial CD, which is a different distribution. It's a cumulative version of the one we've done. So this is option 4. And then variable in order to get just one particular value.